Hello everyone, I'm Colton, and I'll be doing a presentation today with Adia over our project of predictive measures of poverty. Just as a breakdown of what we're going to go through, first we'll go through the introduction, we'll go through some related work that we used as references, the approach we decided to use, and our results. Just for the introduction, the purpose of this project was to develop a machine learning model to apply to global poverty forecasting. The overall goal was to predict household poverty probability across 7 African countries using survey indicators. We attempted to deepen interpretability, validate calibration and generalizability, and explore socioeconomic indicators. The inspiration for this project was from Johnny Yui's poverty prediction project, as available in GitHub. Overall, we look to build a structure that can be used further on expanded datasets. The objective of this project was threefold. We wanted to identify areas most at risk for poverty, identify features most influential in poverty prediction, develop skills for meaningful application of course knowledge, which included cleaning data, performing exploratory data analysis, developing training and test data, and using a decision tree to determine predicted poverty populace. Here you can see some of our motivations, largely for local, state, national, and international policy development. It's important to be able to know what causes poverty in order to stop, these things from happening to people, or so that if it does arise, you can, of course, assist them as best as you can to allow them to get themselves out of it. Some prior work that's been done in this field. You can see here in Microsoft Capstone project, the place where we got the original idea from. It uses XGBoost, light GBM, and gradient boosting in order to make a model. Yui's model in this competition, hosted by Microsoft, landed him in the top 100 in the 40s, if I'm not mistaken. Another model comes from Somalia, which uses RF, DT, SVM, and LR models to predict poverty from demographic data taken from this dataset. And another comes from Costa Rica, once again using XGBoost to outperform proxy means test and reduces inclusion and exclusion errors from this source once again. While high-performance models exist, few focus on interpretability and calibration are some of the things we'd like to take away from this, and some of the things that we would like to improve on. As an overview, the dataset that we use contains 12,600 observations or individuals across 7 countries. It features things such as demographics, age, sex, education, marital status, financial access, such as bank use, mobile money, shocks and income sharing, comes from the financial inclusion insights and the poverty probability index, or FII and PPI. Here you can see a distribution of some of the poverty probability distribution based on some of the variables. Just some of our exploratory data analysis here. You can see poverty based on each of the countries, and or urban poverty versus rural poverty. So this would be rural, this would be urban. In terms of modeling and cleaning up data, we had to drop many columns with missing values, most notably a lot of interest rate related columns were missing almost all of their data, made it practically unusable. And we used some label encoding for binary and ordinal categories in order to make it so that the data was a little bit easier to read, such as changing poverty index to a binary in order to make it more readable from if the poverty index is greater than 0.5, then it's counted as someone in poverty. Some other preprocessing included median imputation using robust scalar and constant imputation using one hot encoder. We can see here some of the accuracies of the models that we made, logistic regression, a decision tree, a random forest, gradient boosting, and XGBoost. Gradient boosting had the greatest area under the receiver, meaning it was performing quite well compared to the other models, though its accuracy was notably lower than logistic regression and XGBoost. XGBoost being the model used by UA and that we originally took inspiration from this from. So you can see here some of the cleanup code, just here dropping these 4 interest rate related columns just due to the number of missing variables that they had, and filling null values with NA in order to still be able to use these variables as they're very important and actually have a lot of important data in them. And of course, converting the poverty probability into a binary, so long as poverty probability is greater than 0.5.
Now, once our data was cleaned, as Colton just described, we were able to then evaluate our models. What you're seeing here is a decision tree. We introduced a shallow decision tree model limited to a max depth of 3 to enhance just the interpretability of it. What you're seeing is one possible structure that attempts to split our training data based on features like access to phone technology, education level, and whether the respondent was residing in a rural or urban community. While this model is easy to understand and visualize, which is what makes it really attractive for a lot of the policy developers that would potentially be looking at model like the one we're looking to create, it has lower predictive accuracy and does not generalize as well as the assembly models that we do go with. So the tree does give us an intuitive entry point to really look at the data, but it is not something to really be used and utilized. Similarly, with the random forest, this is taking a simple slide from a simple snapshot of a 100 branch decision tree that we have, a random forest. Each tray is trained on a random subset of data and features, and assembly makes predictions by averaging those outputs. So by showing a single tree here, we can illustrate how the forest captures more complex splits than the decision tree did. It does perform better than with a AUC of 0.829. But like the tree model, its interpretability is reduced unless we were to visualize further importance using tools like SHAP. So while random forest does improve accuracy, it does come at some of the cost of transparency because you cannot see as much in this little snapshot we have here. But ultimately, that is not of the greatest importance since we decided to use a different model, aka gradient boosting. So using a gradient boosting model, here are some of the diagnostic plots that we were able to develop. They were able to help us validate our model performance. So on the left, we have the ROC curve showing us a high AUC of 0.8, confirming strong separation between classes. The middle plot, the precision recall curve, help us identify an optimal classification threshold below the default of 0.5. So as you can see with this blue dot right here, we have that 0.5 threshold, which is kind of the default, the assumed. However, we were able to determine that it actually fell at this 0.38 is when our model was able to be at its greatest accuracy and the greatest implication. This lower threshold is really due to the necessity to have a higher error on caution since we are looking at classifying people as poor and not poor. And it is better to group people within that poor category versus missing people and assuming misaligning people, misassuming people are not poor when they are poor. Then further, we have our calibration curve. So as you can see, oh, my bad. As you can see with our calibration curve, it is pretty close to that 45-degree indicator, which suggests that our probability estimates are very well calibrated. Meaning that when the model says it's about 70% chance of poverty, it is statistically close to reality. Together, these plots confirm that our model was not only accurate, but well behaved on a probabilistic standpoint, making it very applicable to future use. Here we have just like a little bit more evaluation of that determining of the threshold with the confusion matrix. And then as you can see here, you can see the performance of the model in general using a 0.5 estimate. Um, we correctly identify 88% of poor households using a 0.5 threshold, but only 54% of non-poor households, leading to a high type 1 error of 46%, meaning a high proportion of people are being misidentified as not poor when they are in fact poor. This could greatly divert resources away from people who are actually needing them if this were to be deployed in a actual setting. Hence, we use a matrix of 0.35 as that uh, minimizes the level of minimizes the level of false negatives. Here you just have a coding snippet showing how we were able to develop our curves. What we really see here is the optimization of the F1 score balancing precision and recall. The best threshold, as I have mentioned many times, was identified to be that 0.375 instead of the default 0.5. This adjustment trades off a bit of precision for significantly improving recall, particularly useful when the goal is to minimize false negatives, as is ours. So poor households are not being missed by this model. And here are the final results. So we see here with the optimized threshold, we have an overall accuracy of 0.76 with a strong recall of 94% for identifying poor households. We're able to see a very balanced train test split of the AUC with 0.862 versus 0.825, indicating minimal overfitting. From our feature importance to analysis, we found that education level, rural residency, and access to phone technology were the most influential factors, all of which have intuitive policy-related implications. This reinforces that the model is not only performant, but also aligned with real-world economic determinants. Apologies. And so then where would this research go moving forward? A lot of more advanced research is looking at using satellite imagery of energy uses as well as cell phone data. As we're able to identify some of these factors as very influential, using some of these more robust non-survey measurements would be very beneficial in getting a more detailed snapshot because it captures participants who may not even be able to be accessed by some of the surveyors. Um, we aim to explore fairness matrix, ensuring that subgroups are not disproportionately classified. And we're also working on a version of this model that integrates world development indicators via an API to forecast poverty at the state level. So the data that we used was synthetic data created using the PPI measurements using real estate data. So it is real data that has been synthetically altered in order to create a more malleable uh, malleable use so that students like us are able to actually really look at it and determine some things from it. So using an API, we did try to use that after we had done all of this. However, it was just something way too robust for our computers and would need something a little bit heavier to do. However, the goal would be to do something like that so that you're able to really pool genuine, meaningful interpretations. And using that, we would hope to develop a predictive model that would be able to determine the likelihood of success of investments within different SDG UN Sustainable Development Indicators in order to inform each state's dependence and investment within particular ones. So whether or not they want to focus on education in order to decrease the SDG 1 poverty, all around the goals to alleviate the misallocation of funds and optimize potential results. Um, yeah, and that is our model. As you can see, here are our references. Thank you.